Hi everyone, my name is Bilal Arnaout and this presentation is about our physics lab and circuits. It's lab 3. In this lab we explored how current, voltage and energy behave in electric circuits using fundamental principles like Ohm's law and Kirchhoff's law. So the main goals of this experiment were to understand the conservation of charge and energy, compute current and voltage in various circuit setups, and analyze how capacitors charge and discharge over time. We also compared our measured data with theoretical predictions to identify any sources of error. The experiment relied on three main physical laws. First, Kirchhoff's law's loop rule, which states that the total voltage change around any closed circuit loop must be zero. Second, Ohm's law, which relates voltage, current, and resistance through the equation V equals I times R. And finally, the RC circuit equation, which describes how voltage across a capacitor changes over time as it charges or discharges. Now, for this experiment, we used two 1.5 volt batteries, two ammeters, and resistors of 147 ohms. We measured the current and voltage across each resistor and calculated the total voltage drop in the circuit. Later, we also built an RC circuit using bulbs, batteries, and capacitor, allowing us to observe how the capacitor affected the overall behavior of the circuit. The system included everything inside the circuit, like the wires, batteries, resistors, and capacitors. The surroundings were the air, the table, and our measurement devices. To make sure our results were accurate, we checked that the batteries were properly connected, nothing was interfering with the current flow, and the experiment was done at room temperature. Comparing our data with the theoretical model, we expected a total voltage difference of 0 volts, but we actually measured 1.44 volts. The capacitor's discharge behavior matched our expectations. It started bright and then dimmed as time went on. The observed discharge times of about 37 seconds in one trial to 9.6 seconds in another. Small variations were likely caused by temperature, loose wires, inaccurate readings, or battery wear. Now, some key questions came up during the lab. First, why did our measured values differ slightly from theory? That's likely due to resistance in the wires, battery depletion, and instrument precision. Next, how does connecting a voltmeter affect the circuit? Since a voltmeter has a very high resistance, it draws almost no current, meaning the overall circuit current barely changes. And finally, our real-world result varied from ideal predictions because of small experimental errors and imperfect component behavior, which is expected in physical setups. When we added a new voltmeter and used the existing ammeter, the readings were 0.02 milliamps for the ammeter and 2.7 volts for the voltmeter. The ammeter's small reading reflected the effective resistance in that section of the circuit, while the voltmeter measured the potential difference across the components. Now, according to Kirchhoff's law, the total potential difference should add up to 0 volts. However, in our measurements, we found a difference of about 4.4 volts, which we attributed to small imperfections, devices, calibrations, or environmental effects. Now, when we test the voltmeter, the ammeter reading barely changed. That's because voltmeters have extremely high resistance, so almost no current flows through them. As a result, the total current in the circuit stays nearly the same. Before replacing the voltmeter, the current was negative 11.9 milliamps. After replacing it, it was negative 11.2 milliamps. This small change happened because the parallel current path was negligible, meaning the circuit's total current remained only nearly constant. Overall, the data confirmed the theoretical predictions with reasonable experimental error. Now, to close up, to sum up, this lab helped reinforce circuit concepts like Ohm's law, and along with that, Kirchhoff's rules and the behavior of RC circuits. We also learned how small experimental imperfections can cause effect results, emphasizing the importance of accuracy in real physics experiments. Thank you for listening.